everybody. Looks like the audio is okay. Barely River Jr. back with another Science Hour. As promised, we'll do a part two of a stream from a few weeks ago where we did the gravitational potential of the planet Earth and our orbit around. So basically, we did the satellites around Earth and Earth around the Sun. The link to that should be in the description, so check the description. You'll be able to see the link to the background of that. So I won't cover the background in detail, but if you check that that stream, you'll be able to see what we're doing today, as well as the derivations that we're applying. It looks like something happened with my. Oh, well, I have to fix whatever happened with my. See, hold up. Just this briefly. To be fixed on the on the screen. All right, that's better. I adjusted my other screen, but I forgot to adjust this one. Awesome. So we'll look at some applications of what we did on that stream. You can look at the description. I believe it was Science Hour number 6. It is in the description, part 1 of this one. We'll jump right into it and see what we have. So the idea for today, I was thinking about exactly how to do it. And the idea simply came to look at the solar system and the orbit of the solar system and basically apply what we've already proved a few weeks ago, which is how it's done in real life as well. So I gave a talk on dark matter and dark energy, I guess it's like a year or two ago now, and we talked about the distance scale and how we confirm parallax. And then after we confirm parallax, so basically parallax we've spoken about before here as well. You have the Earth going around the Sun, and the angle it takes for a star to have 1 arcsecond of angle due to parallax. That star is 1 parsec away. And so what we did was we got distances to stars with things like parallax, and then we observed something else that we can use, like a supernova. I used to call it a type Ia, is actually properly pronounced type 1a. They have the same luminosity when these types of supernova explode. These are the ones that explode because there's a binary star system. And the companion, so let's say we have a star that died, so it's a white dwarf. Many stars, when they die, they become white dwarfs. It's like a core of, let's say, carbon, and it has a companion star that's a real star, but this star is actually close enough to where it's leaking matter to join that star, and when enough matter leaks onto it, it could ignite and destroy this entire thing. And the mass at which it explodes in that way is about 1.4 solar masses. So since it has the same amount of solar mass and usually the same amount of material, usually carbon if I recall, so basically a large enough star that fuses helium to hydrogen, then hydrogen to another element, and so on and so forth. And when it gets to carbon, or the star's fuel has ran out by that time due to the size, and this carbon thing explodes, and it has the same luminosity because they're all about the same size. So now we can go ahead and focus on these type 1a supernovas to get distances to even farther things, because we can see these, for instance, in other galaxies, but we can know the distance to them because we measured it with parallax. We know how bright they are. We know how far the close ones are. And we can go ahead and use the luminosity to magnitude relationship to distance things in other galaxies by seeing supernovas explode in them. So you can see how we verify this first step, the parallax step, We use this parallax step to verify the type 1a supernova distance. And then we went ahead and took the type 1a supernova distance and to verify the distance to a galaxy when we see one of these explosions there. So sort of like a step ladder. That's why they call it the sort of cosmic step as far as measuring distances. So by the same token, we can look at the Earth like we did in the stream, the part one of this stream, and we know that we take a year to go around the sun. We use radar to see how far away we are from the sun. So we know that this distance is about 93 million miles. We know it takes 365 days. So we can go ahead and get a velocity that we are going around the sun for. Um, and that velocity, what do we get? Scrolling through what we did previous weeks. This must have been our quantum week. So we got, just do one, 29.8 kilometers per second. This is the week. Maybe I'm looking at the wrong one. I remember having a drawing of the Earth there. Here we go. Yeah, so 29.9 kilometers, about 30 kilometers per second. That's how much we got for the speed of the Earth around the sun. And we also verified with gravitational potential that we get the same answer. So you confirm that gravitational potential works by measuring it relative to something that we can measure very directly by just simply looking at the rotation of the Earth around the sun. And like I said, we do the same thing with distance measurements with parallax and type Ia supernovas. So we can go ahead and do the same thing with potential. So this is a NASA site that talks about the solar system, and it gives some details. I'll read the first paragraph. Introduction: our solar system includes the sun, 8 planets, 5 officially named dwarf planets, hundreds of moons, and thousands of asteroids and comets. Our solar system is located in the Milky Way, a barred spiral galaxy. So we understand now that the Milky Way in the center, and a professor came and spoke a week or two ago and clarified that it's understood to be a bar galaxy with a few bulges in the bar. So this is a slight bulge, it's like a double bulge, but it's not necessarily a circle. There's a bar shape in the center. And with a bar spin galaxy with 2 major arms and 2 minor arms. So it's like I technically drew the right amount of arms, maybe one less, but perhaps 2 of these will be smaller, the minor arms, and 2 will be bigger. So we have 2 major arms and 2 minor arms. Our sun is in the small partial arm of the Milky Way, while the Orion arm, so we might be, for instance, here, or Orion spur, between the Sagittarius and Perseus arms. So I'm not sure which one of these are Sagittarius and Perseus. Our solar system orbits the center of the galaxy at about, so this will be our velocity, about 515,000 miles per hour. Now, so let's do the kilometers. 828,000 kilometers per hour. And it takes about 230 million years to make one complete orbit around the galaxy. And no doubt they got this from simply observing the galaxy and the various satellites and telescopes we have, and extrapolating that rotation that we observe over time. So what we can do is we could apply the formulas that we have here to determine the how much mass is in the center of the galaxy relative to our radius. So that's why I was mentioning last week. I was a little bit complicated because there's mass within our orbit and outside of our orbit. So, for instance, using this formula, we're basically looking at the mass within our orbit that's affecting our uh, uh, revolution around the galaxy. And also, it's slightly more complicated because if we have like a spherical distribution of mass, then the only thing that affects how much mass is being affected is the radius. So, for instance, this amount of radius will only be affected by this amount of mass, and this amount of radius will only be affected by this amount of mass. But if we had an uneven distribution of mass, let's say like this, well, I can't do that same determination because this spot here, it'll still be getting affected by all of this mass, and there's only a little bit of mass on this side, so it makes things a little bit more complicated. So the fact that the Milky Way galaxy has two large arms and two small arms means that even this will be an approximation because, for instance, however far this arm goes out, it's affecting the pull over here as well. So, but what we'll do is we'll just make a simplification out of this, and we'll just treat the galaxy as if it's a symmetrically even galaxy, and we'll just uh, treat the center as a orb or bulge that's symmetric, and we'll just treat the arms as if they are equal length and density. So this is a simplification, but we'll see what we come up with. We learned a few weeks ago that when you have the gravitational potential, that's in the units of meters squared per second squared, and the square root of that will give us the speed. So we did that when we got the speed of the Earth around the Sun and the satellites around the Earth. So we have here square root of I, and we just discussed the satellites, but there's the Earth one. Square root of I matches. So all we have to do is take the square root of I, that's I copied that down earlier, and then we have the velocity. So let's go ahead and look at this. So we have V equals square root of I, or psi really, going to be square root of G M sun or a galaxy. That gives us two unknowns. Let's see if, oh well, we're treating it as a symmetric thing, so we could easily get the radius. So then we'll say that V squared equals G M naught over R galaxy. And we can solve for the radius with this simplification. So we'll say the mass, and I'll say mass CG, mass center galaxy, center to center from us, equals V squared RG over G. So this should give us a rough estimate of the amount of mass that's at a radius less than, even slightly less than, the radius of our distance from the center of the galaxy. And let's go ahead and work out the radius so we can actually use, what is that? Trigonometry, geometry. So basically we have a circle. We have the period, or the time frame is 230 million years. The distance is 2 pi r. And we have the speed is 828 kilometers per hour. So check, make sure everything's streaming properly, by the way. Things seems to be going well. If there's any audio issue or something, let me know. Right, so let's see how we can use this. So why don't we find a convenient conversion of years to seconds. Oh, well, not too hard to just do the math real fast. We have 230, like 0000000. And the proper way to do this is years, and 1 year is 365 days, and 1 day is 24 hours, and 24 hours is 60 minutes, and 1 minute is 60 seconds. So we multiply this out. Right? So that equals 7.25, to average a bit, 10 to the 15 seconds. So that's how long it takes to go around the sun one time. And maybe I should have made it hours, since those are in hours. Divided by 60 will give you a minute. 60 will give me hours, so let me make it into hours. So that equals 2 point, oh, well, we round that to 2 easily. 2 times 10 to the 12 hours. So we have 8. To get the distance. So we have 828,000 kilometers per hour. We multiply that, so I guess we can actually say km per hour. And we multiply that 2 times 10 to the 12 hours. We get 1.66 times 10 to the 18 kilometers. So that's how uh, long the orbit is, the orbit of our cycle around the galaxy. So now since we have that, so again, you can say C is the entire way around. So C equals this, and we can say C equals 2 pi r when we're dealing with a circle. Again, we're approximating it like a circle. So r equals C over 2 pi. So that's going to be 2.655 times 10 to the 17 kilometers. So that should be the radius. So basically what this means is I have r g, our radius or distance in the galaxy, distance from the galactic center equals r. All right, so we have that. And I think we have everything we need now. You can say the mass in the center of the galaxy is v squared times rg over g. And this is going to be in units wise, meters squared over seconds squared. This is kilometers. And what are the units of g again? So actually I have those up in here somewhere. Let's see. This g. So this is meters cubed over kilograms times second squared. So the second squared will cancel. The meters cubed, there's meters cubed on the top and meters cubed here will cancel. And that will leave us kilograms. So that means our formula is right. Our units come out right. So you could say mcg equals, and the velocity was 828. And I'm getting it from this site here, 828,000 kilometers per second. This is going to be squared. I have to remember to put 10 to the 3. I'm going to write that down. 10 to the 3 meters per second squared. The radius is going to be 2.655 10 to the 20 meters, because I have 10 to the 17 kilometers, and kilometers is 10 to the 3, so I'll just make that 10 to the 20 meters. And we're dividing by, and I'll just copy this over. 6.6743 times 10 to the negative 11 meters cubed over kilogram second squared. That's a gravitational constant. Let's see what we come out with. The last week we talked a little bit about the difference between the Coulomb force and the gravitational force, and the very small size of the gravitational constant is a testament to how small the gravitational force is. Otherwise, if you look at the Coulomb constant, it's like 10 to the 8. So the fact that the constant that governs that dynamic in the universe, the size of that constant dictates how much the force, how much impact the force has. And this comes out to be 3.293 times 10 to the 39 kilograms. Right? So why don't we find this in solar masses? And I believe I had to have solar masses in here somewhere. So I did solar masses and we did the solar system thing. Okay, here we go. Solar masses is this. I got that from the NASA solar sun fact site. Pretty good site. So we have 3.393 10 to the 39 kilograms divided by 1,988,400 times 10 to the 24 kilograms. Let's see how many solar masses this gives us. So basically, you divide it by the sun's mass, and we know what solar masses we're working with. We have 1,988,400 1024. One point 6565 times 10 to the 9 solar masses. So what is that? That's 16 16 and a half million, 16.6 million. I'm looking at, oh, that's trillion, no billion. Not even 16.6. That's going to change it. 1.7 billion solar masses, if I'm reading that properly. We have yeah, right. So utilizing what we confirmed with the solar system, how the gravitational potential accurately determines our uh, positioning, given we understand or know the mass of the sun and the radius, we confirm that. And maybe one day we can do the mass of the sun and the. Actually, I think I did that already. If you look at one of my older streams under the previous show brand name, we did the calculating the solar mass. Because basically you can get that with Kepler's laws, but Kepler's laws using Newton's equations. So basically, we know that, remember the formula, E squared equals A cubed, and this is the period, and this is the semi-major axis. Basically, this is one of Kepler's laws, that the square of the period of a planet orbiting the sun equals the third of this distance from the sun, because the sun is basically, the orbits are basically circular. So we could approximate that as just a circle. The semi-major axis is basically the average distance from the sun. We could easily calculate and predict all the positions of the planets. But utilize any more advanced formula, just look for that previous video. We did that one week. And you can see how we can get the mass of the sun because these orbits will have a certain rate based upon the masses involved, and the mass of the sun is so large it overshadows all the other masses, and we could basically extract the solar mass, considering the planetary mass is insignificant. Even though the mass of the sun, that's what was able to use that to confirm that the velocity and distance we observe just by observing the solar system matches what we calculate with gravitational potential. Thus, given the range of this approximation, so again, we made a few approximations on this calculation. We approximated the galaxy as uniform rather than having a long arm and a short arm, with us on the short arm. We approximated it to be spherically symmetrical rather than a bar. So we made some approximations here. But given those approximations, the amount of mass within or closer to the center of the galaxy to us is going to be about 1.7 billion solar masses, and that's including all the stars, the gas, the dark matter, all the different masses that's contributing to the gravity that's keeping us going around the solar system. Going around the galaxy at 828,000 kilometers per hour and taking 230 million years to orbit the galaxy. So that's one way to apply that. And it's pretty straightforward. So let me know if you have any questions. Might be a short stream today. Did a few long ones or previous ones. So nobody that has any questions, I might close up in a bit. I'll give you all a few minutes to see. If y'all want to type anything, any questions or comments. While y'all are thinking about any questions, semester's going okay. I have some exams about to come up soon, so I've been preparing for those. Wish me well. And hopefully I do well on all my classes this semester as I did the previous ones and go ahead and graduate and all that good stuff. Which reminds me, I think I have to apply to graduate or something. I have to look into that. Maybe I need to do that now before I forget. So also it looks like there's no questions coming up at the moment. Thank y'all for joining. Carol Lee Barber Jr. out. I'll be back next week. Not sure what the topic will be. Maybe I'll work some problems. Maybe we'll look at a concept. I know coming up soon, I'll be finished my preliminary research on the Persephone cluster. So pretty soon I'll be giving a presentation on that. I've already talked with MC Toon on chat, and we'll work out a date where I'll go present on this channel like I did for the Dark Matter Dark Energy talks. And I'm also asking some others as well. So look forward to those. Those dates will come in the future. Thanks everybody for joining. You'll have a good evening.